Hello everybody and welcome. In this video we're going to look at Cayley Hamilton theorem. So this theorem states that every square matrix is a root of its characteristic polynomial. That is, every square matrix is a root of its characteristic equation. Sorry, it should be equation, not characteristic polynomial. So it should be characteristic equation, because we can only have roots of equation. Okay, so that's what Cayley Hamilton theorem is all about. So it says that every square matrix is a root of its characteristic polynomial. So what is a root? Say for instance you have an equation x squared minus 3x plus 2 equals 0. Those values of s, that when you put them in this equation you are going to get 0. They are the root of this equation. So 1 is one of them, because the root of this equation is just 1 and 2. So when you substitute 1 to this equation, we have 1 squared minus 3 times 1 plus 2. So that will give you 1 minus 3 plus 2, which is going to be minus 2 plus 2. So and if you substitute 2 to that, we have 2 squared minus 3 times 2 plus 2. That will be 4 minus 6 plus 2. That will be minus 2 plus 2. So these 2 and 1, okay, that is substitute to this equation to get 0. They are the root of that equation. So that means for every square matrix, if you find its characteristic equation and you substitute that matrix in that characteristic equation, it means the matrix will be equal to 0 according to Cayley Hamilton. So now let's try that. Let's look at this matrix A equal 1 minus 1 minus 6 minus 2. So let's look at this equation, this matrix, and let's use it to verify the Cayley Hamilton theorem. So if you want to find the characteristic equation of a 2 by 2 matrix, it's going to be lambda squared minus trace lambda plus the determinant of that matrix equal 0. So that's how to find the characteristic equation of this matrix. And what is the trace of that matrix? So when we say trace, the trace of a matrix is the sum of the diagonal elements. So here we're having 1 and minus 2. So when you add them together, you get the trace. And in this case, it will be 1 minus 2, which will be minus 1. And the determinant of that matrix is simply the product of this minus the product of this. So that will be minus 2 minus in bracket of minus 6 times minus 1. That's going to give you plus 6. So you have minus 2 minus 6, which is equal to minus 8. Now you can get your characteristic characteristic equation. Lambda squared minus the trace is now minus 1 times lambda plus the determinant is now minus 8 equal 0. So that will be minus lambda squared plus 1 lambda minus 8 equal 0. So this is the characteristic equation of this matrix. The matrix is 1 minus 6 minus 2. So for this matrix, let's try and substitute A, which is matrix A, as given. So let's try and substitute that for this lambda in the characteristic equation. So let's say we have A squared, then plus, anywhere we see lambda, we put A, then minus 8. Now since A is a matrix and this one too will be a matrix, A squared will be A, will be A times A. So since when we multiply two matrices, we are still going to get a matrix. So it means this is a matrix, this is a matrix. So we need to express this 8 in form of another matrix itself. Now normally 8 will be 8 times 1. So now in matrix form, it will be 8 times this I, which is the identity matrix. It's like the 1. Okay. So now when you multiply and so let's find A squared, because we already know A already, and we know the matrix I, which is just I is an identity matrix, and for 2 by 2 matrix that will be 1 0 0 1. Okay. And to find, we have known A, we have known the identity matrix as well, so we need to find the A squared. So for A squared, we're going to have 1 minus 1 minus 6 minus 2, okay, times another A, 1 minus 1 minus 6 minus 2, okay, and we're going to multiply the two of them together. So you use this first row to multiply the first column. So we have 1 times 1, that will be 1, plus this times this, which is 6, so that will be 7. Then this times this again, so this first row times the second column to get the first row second column element in the new matrix. So that will be 1 times, okay, that will be minus 1 plus 2, that will be plus 1, okay, minus 1 plus 2, so that will be plus 1. So this one will be minus 6 plus 12, so that will be plus 6, and this one will be 6 plus 4, so that will be 10. Okay, 6 plus 4, that will be 10. So we have this as our a square, so we put it here, so the a square will become 7 1 6 10, then plus the a, which is 1 minus 1 minus 6 minus 2, and minus 8 times I, which is the identity matrix. So let's see, maybe this will be equal to 0. If it is equal to 0, it means that definitely the root of that equation is actually the matrix itself. So we have 7 plus 1, that will be 8, 1 minus 1 0, 6 minus 6 0, and we have this minus this, we have that to be 8. Then minus, when you multiply 8 with all this, we have 8 0 0 8. So when you subtract, you are going to have, all you have is just this minus this, 0 minus 0, 0 minus 0, 8 minus 8. So that means this gives 0. So it means that the characteristic polynomial of this matrix, its root, one of its roots is the matrix itself. So we can now see that for every square matrix, okay, every square matrix is a root of its characteristic equation, and that's how to verify this CARLEY Hamilton theorem. So this is very useful for finding the minimal polynomial of a matrix. So I'm going to see that in the next video. Thanks for watching, and don't forget to subscribe to this channel and share this video to your friend. Like and subscribe to this channel today. Thanks for watching.